Welcome back to the series. Last time we got the machine working, all the logic is working, but we still have the ripple in the 5-volt line. I was using my bench power supply in the previous episode. Now the fuse is back and I'm using the actual switching regulator built into the die, and look at what it does to the video signal. Not only is this ripple bad for the chips, it makes the video signal unusable because it modulates the image. So we have to do something about it, and I don't know what else I can do. I decided to try adding yet another bypass capacitor, 2200 microfarad. That's a lot, even more inrush current. I thought I'm going to add it to the composite mod video so it stabilizes at least a little bit the image, even though the rest of the circuit will still suffer from ripple. I decided to put it in with an extra 47 microfarad tantalum capacitor bodged right on the composite mod. A lot of inrush current there. I'm not happy with this, but yeah, still didn't solve. So I decided to look at the one piece I didn't look at yet, the inductor. Let me show you the noise that the inductor makes. I already desoldered and tested this inductor for continuity. There is continuity, but it vibrates a lot because the core is loose. And I'm beginning to suspect that it may have something to do with the fact that there is so much ripple in a switching power supply. Half the time the current provided to the circuit comes from the rectifier, and the other half of the time, when the pass transistor is off, the current should come from the inductor, when the magnetic field of the inductor collapses and translates into current that goes to the computer. I'm beginning to suspect that there may be some short circuit inside the inductor, and it's not playing that role well. But inductors just like these are not made anymore. I'll try to find a replacement, and I'll try that out to see if it improves. But for now, let me just show you the noise this makes. I think this noise has to do with the fact that the core is so loose and the winding is also loose. But yeah, that's one thing to do. So I desoldered the inductor to actually measure the inductance. You might say, well, we should have done it before, and I should, but these things are usually bulletproof. So let's see now, it should be 1 millihenry inductance according to the schematics. And we get half of that. We get 500 microhenry, exactly 500. So what is the chance that an enamel failure would lead to exactly 500 microhenry? I think this was just a smaller inductor, that it doesn't have enough windings. I think it was the wrong inductor to put in there, which is consistent with the picture of this die having been a factory refuse, a sort of a hack. But yeah, I managed to find another one that looks completely different. It's a toroidal inductor, but it is 1 millihenry. So that should help a little bit. I can't keep on increasing this inductance beyond 1 millihenry because you pay a price for that. You know, the flyback current starts becoming huge, a lot of voltage potential that the flyback diode has to compensate for. But yeah, 1 millihenry, that's what is in the schematics. So let's put it in and see what happens. At the very least, at the very, very least, that noise will stop because this new inductor, the windings are not loose. There is a coat of varnish in there that holds everything together. So at least that we have. So solder it in. It should be simple. There it is. I had to extend one of the terminals a little bit, but it fits very nicely. It's a matter of now, testing to see how much this will reduce the ripple. It will reduce the ripple for sure. It's twice the inductance, but I don't think it will help very much. Let's see. I'm ready with my oscilloscope probe to measure the 5-volt rail at one of the memory chips. And there we see that there is still a lot of ripple. I'm in DC mode on my oscilloscope right now. There is visible ripple. I'll go to AC to have a look if I zoom in and have a look at only the AC component, only the ripple, we still have quite a bit, well over, that's over 200 millivolts. should be under 50, and the image is still dancing all over the place. So yeah, it did help, you know, from 300 to 200 millivolts. Yeah, it did help, but clearly just adding more inductance will not alone solve this. I would have to put a couple of millihenry inside that power supply. Not sure it would even fit. I quickly have a look at the other signals, especially the RAS and CAS, to make sure that those are not problematic. We went through a lot of troubleshooting to correct those signals before, and now they are okay. They are still okay. They will be okay. So the problem really is the ripple, how bad it is for the chips, and how bad it is for the image, because it modulates the image. I'm typing in a little program in BASIC, so we have more reference points on the screen to be able to judge how legible or illegible the image is. I'll do that with my old retro phone. There we go. That's the inductor right there. Yeah, this is definitely not usable. I wonder if this machine ever was usable, because a 500 microhenry inductor there, yeah, was this ever really usable? Maybe not. Maybe this never really worked. I tried one more Hail Mary. I changed 2 of the resistors in the power supply circuit for the values that are on the schematics, as opposed to the values that were there originally. But it didn't do much. Everything is still dancing left and right. So yeah, at this point, I was about to give up on this thing. It's so much frustration. This power supply is such a nut job. I changed the wire gauge for the flyback diode in case there wasn't enough capacity for current, but that didn't do anything either. And so I finally decided to modify this power supply. You're my witness that I did my best not to do so, but it is required. That's the modification. It's very simple, very robust, very elegant, and it works, and it applies only to the 5-volt rail, not the other 2. Here's the mod. It's pretty simple. The device you will need is a Meanwell NID 35-5. You can buy this, I don't know, 15 euros, maybe a lot less, 10 euros maybe. I bought this one at Distrelec. It's in the Netherlands, but you can find this probably at Mauser, DigiKey, anywhere. It's a non-isolated DC to DC converter. It can take up to over 50 volts on the input. It produces a stable 5-volt output at up to 3.5 amps. Here you can see that the 5-volt rail is indicated at 4 amps, but this is for a completely fully populated die, and even this has some sandbagging. So this device here will do. Now you will need to solder, well, you don't really need, but it's a good idea to solder these 2 pins together. These both are V in, the input voltage. If you solder them together, you get more oomph. This here to the side is ground. The first one on the other side is also ground. And the other 4 are V out, which is the 5-volt. So that's basically what it is. Notice the orientation. This board is populated on both sides. I'm showing you the profile of the components that are on the side facing you. So you get the orientation right. Another way to make sure that you have the orientation right is to notice that on this side there are 6 pins, and on this side there are 5 pins. So get the 6 to the left and the 5 to the right, and you have the correct orientation. Now it's a good idea to join these together and these 4 here together, because then you get the maximum oomph both for V in and V out. And then the next thing you do after this, if you want, it may make it easier to assemble it, you get rid of the first 3 pins to the left. You will not need them. You can cut them if you like. Then you need to connect 2 capacitors. These are the values I recommend. 100 microfarad between V out and ground, and 22 microfarad between V in and ground, and 22 microfarad between V out and ground. Here you have V in, this pin here, and the 4 pins to the other side are V out. That's where they are. So connect these two capacitors. Don't forget to take a high-rated capacitor as far as voltage is concerned for the input side. The voltage you get there is 22 volts DC. It can go up to 25, but it's a good idea to oversize it. On the other side, you get 5 volts. 25 volts is nicely oversized. 16 volts would do as well. So now we have both capacitors connected. Next thing we need to do is to remove the switching controller, the SG3524. In my case, it was already socketed, so I just pulled it off the socket. As simple as that. And you want to do that because otherwise you will get a base bias here on the Darlington pair, and you don't want that. So get rid of this, remove it from the board, put a socket and leave the socket empty. And I recommend that you desolder the inductor as well. Not only does it make space, you cut the connection between this point and the collector of the Darlington pair, which is not strictly needed, but it's a good idea to do that. It will be safer this way. So now that you've removed the switching controller and the inductor, you can connect the NID35-5 to the PCB. How do you do that? Well, the first thing you do is this pin here, that's V in. And you want to connect V in to the output of the rectifier, or which is what I did, to the positive side of this bulk capacitor of 4,700 microfarad. That's where I put it. It's very easy to access. I just connected it to the lead of the capacitor. The next thing you need to do is to connect ground. Now ground is here and here. So we can choose one of them. I chose this one and connect it to ground. And you can connect to ground anywhere. I'm showing here the other side of this C55, but you can connect to ground anywhere. I found an empty pad on the PCB that was close by, so I connected ground there. Now these 4 pins here, they are V out, and you need to connect them here to the correct side of the fuse. And the video showed you, or will show you on the board, where to connect this. You can use an empty pad as well. There was one when I removed the inductor. This pad here became free. You could connect it there if you like. I didn't. I wanted to leave those 2 pads free to make sure that this mod is as easily reversible as possible. So I connected it straight to the fuse holder, but connected to the right side of the fuse holder, the side that is closer to the keyboard. And this is it. This is pretty much it. That's the mod. You know, the 2 big things are to desolder the switching controller and the inductor, although the inductor only 2 terminals, how difficult can it be? And then to assemble this thing here before you connect it to the main PCB. As easy as that. Just make sure you use this device, the Meanwell NID35-5, because that's the one that can give 3.5 amps. You cannot use those Traco powers because they can give you 2 amps in the case of the bigger ones. You need a proper DC to DC converter that can provide a sufficient current. This is an example that will work. That's in my experience. I don't know for any guarantees. I haven't tested this for weeks. I just put it in there and it worked. I used it for several minutes, maybe an hour. So I cannot guarantee anything, but this is what I did. And it did work for that hour. I see no reason why it shouldn't work, indefinitely. But again, I don't give you any guarantees if you ruin your DAI. Here's the data sheet of the NID35. The one you should use is this one, NID35-5, which produces 5 volts on the output, up to 3.5 amps. Here you see the rest of the specs. There is only one thing you should pay some attention, and this is this external capacitance load. And you see that the maximum capacitance load is 100 microfarad. Now, what this means is that if you connect this DC to DC converter to a circuit that has a lot of capacitance, when you're charging those capacitors, as soon as you turn the thing on, there will be that current inrush to charge the capacitors at very, very low impedance. And this may trigger the overcurrent protection of this device. So to guarantee that you will not trigger the overcurrent protection, you cannot hang more than 100 microfarad. Now, how much capacitance do we have? We have a lot more than that. It's because this number here is sandbagged. If something goes wrong, Meanwhile doesn't want you to blame them. They want you to blame yourself. In my experience, you can put a lot more than 100 microfarad, and it will not trigger the overcurrent protection, because even the traces on the board leading to the different tantalum capacitors have some resistance. Now, what I did do, I removed that extra bulk capacitor for 4,700 microfarad that I had put there originally to try to control the ripple. I also removed the other one I put on the video card, 2,200 microfarad. It would be too much, I'm adding like 8,000 microfarad. So that's too much. I removed both of them, but I left the oversized tantalums that I had put on the board on the 5-volt rail. So those add up to more than 100 microfarad, but it's okay. In my case, it works. I believe it will work in your case as well. And you can see here that the input range for voltage is between 10.5 and 53 volts DC. I'm feeding it 22 volts DC from the full bridge rectifier, which I'm taking on the positive side of the bulk capacitor. So that falls more or less in the middle of the range. So that should do. So yeah, this is the device you want, the NID35-5. So here's how you connect it. I put a wire, a large gauge wire, on the positive side of the bulk capacitor, the 4,700 microfarad one, and that goes into the V-in of the NID35-5. Now that's the ground lead that goes to an available pad that was down there, very close. And this is the V-out lead that I could have used a pad from the inductor, but I decided to wire it underneath the cage directly to the fuse holder, as you see there, to make this modification as easily reversible as possible. Now the switching controller is not there and the inductor is not there, but if you do this mod, you just keep them and the modification can be reversed. Now let's look at the result. There is our little modification. I'm putting the oscilloscope at the input of the fuse on the 5-volt rail as close as possible to the power supply. The whole thing is looking good. And look at that. A completely stable image, even though I removed those extra filter capacitors I had added. No ripple. Yay! Finally no ripple. And that's what you see on the oscilloscope. That's the 5-volt rail. Solid. It's 1 volt per division. It's solid. I'm going to go to AC coupling so we can see only the ripple. I'm centering it again. Now I'm changing the resolution down to 50 millivolts per division. And look at that. The ripple is under 20 millivolts. From well over 600 millivolts originally to under 20 millivolts. That will do, pig. That will do. And the image bears witness to the fact that there is no ripple. And since the switching transistor is now effectively inactive at all times, it's never biased into activity, it's pretty cool, as you can see in the infrared. Only one of the linear regulators gets a little bit warm next to it, but the switching transistor to the left is very cool. So this mod also has some thermal management advantages as well. That's our little mod. It doesn't even look bad, does it? Some of the metal is exposed, so I'll have to deal with it. You will shortly see what I did. But it doesn't look half as bad. It looks almost like it belongs there. All right, now I'm going to put some hot snot to prevent any short circuit with the cage or with other components. I'm going to put a little bit of hot snot between the board and the transformer, so the board doesn't move around and doesn't go down and touch the metal of the transformer. And then I'm going to put some hot snot across the leads to make sure they don't touch the top of the cage once I close it, or to make sure they don't touch one another either. This should make it mechanically pretty robust and electrically insulated as well. Once the hot snot dries, it becomes more equal, more uniform, and that's the final appearance of it. And it's pretty solid in place, not only because of the hot snot, but because of the high gauge wires I used, not only to make sure that enough current flows without without much resistance, but it also has a mechanical role. So it's finally the time, the ritual closing of the PSU's cage. Hallelujah! It's finally done. I was looking forward to this. And now it's my very favorite part, my most favorite part. It's time for the final touchings. These two chips related to the keyboard, to which all the keyboard bodges are connected, I put brand new chips in there because imagine if one of these chips goes bad at the museum and it needs to be replaced. It's a lot of work. So to prevent that, I put brand new chips there that will last for the next 4 decades at least. And instead of that ugly tape, which is not very reliable either, I'm using some hot snot as a strain relief to make sure these bodges don't come off. The glue will not stick the chip to the socket, it will just stick the bodge wires to the pins and make sure that they don't come loose. I left a little bit of tape for the reset cable on the other side because I thought tape was good enough for that. And once it dries, that's what you get. It's not the most beautiful thing in the world, but it's certainly less ugly than Kapton tape. And it does its job very well. It will secure those bodges there. Also important, the back of the keyboard, I put a lot of hot snot on those numerous cables that go in there. They are also bodged in a more or less precarious way. Now I noticed that the character memory gets a little bit warm. Not too bad, but you know, why not? Put a heatsink there. I also put some heatsinks on 2 SRAM chips that are off to the lower right of the frame. You can't see them, but I put heatsinks there as well. And heatsinks do work. Just look at the infrared picture of the same character memory with the heatsink. It's much better, so it will last longer. And now, since all the soldering and this soldering is done, I thought I'm going to apply a conformal layer to the back of the board. I'm using Flux Varnish LT4 for that. You can still rework the board with this. If you put a hot iron on a pad, the Flux Varnish will just melt and in fact work as flux. But you know, you don't want to put this conformal layer while you're still doing a lot of rework. But now that the rework is done, I thought I'm going to protect it because the solder mask came off in several points. It was already off in several points. So I added this extra protection. And as it dries, you can see it becomes pretty glossy. I leave it to dry for a day. And it looks very good at the end, and then the board will last longer. It also fixes that factory bodge, little red wire that you see there. It fixes it in place. And to finish off the PCB, I'm adding a little note so people know when this board was restored for the last time. And now it's time to put the whole thing back. Finally, these boards will come back to the case. There are a few screws. Most of them were missing when I got this machine. I'm replacing them with nylon screws so you don't have metal rubbing on the plastic of the case and could deteriorate that plastic. So I'm using exclusively nylon screws to put it back. With all the work done, look at how nice it looks. Just take some time to enjoy this. let's continue with the final touches. I'm applying 303 UV protectant to the keycaps. The keycaps look like they are marbled, but that was not me. I didn't try to retrobrite them. I only retrobrited the space bar. Everything else was the way I got it, and I'm just trying to protect it a little more. The space bar in the original die was black, so this light gray space bar, it comes from a much later version of the DAI computer, an Inductor version. And I think the original was lost, and they just sort of cannibalized a newer die for that space bar. At least that's my conjecture. That's what I think happened. I'm now closing the rest of the case. I saw a comment from one of you in one of my previous videos. I was talking about the keyboard having been replaced at the factory. Someone said that actually the original keyboards were very fragile, and that the keyboard I have could indeed have been an aftermarket modification. I still think this is a sort of factory refuse die that some die engineer decided to save money and use, try to fix the problems in it, because there are too many other things that indicate this, like the board is not fully populated, the pedal ports are not populated, the second tape port is not populated, the audio port is not populated. So this was a bare minimum die made to be used with a monochrome monitor in a professional setting. That's why I think it was sort of a customized out of factory refuse. Now I'm using double-sided tape to put the two metal components of the case back. This should facilitate the life of the next conservator. If I would use dirty liquid glue, it would be much more difficult to remove these things later. This double-sided tape I'm using from 3M, it's very strong. Things will not detach unless you do it intentionally with a plastic spatula. But using a plastic spatula, you can easily remove it. So the life of the next conservator a few decades from now will be easier than mine. And a final polish. And we are ready now for the reveal of the cased die. And this brings us to the end of this series. Thanks for being with me in this exhilarating journey, sometimes frustrating, but certainly worthwhile. Now, I know many of you would have liked to see more architecture details, maybe see the machine in action in full color and graphics, to understand why I said that this machine is so great in terms of its logic. But I am reserving all of this for a future series. I don't want to share more details of those plans, but you will see when it's out. Just give me a few months. I need to return to Talos now to complete that project, and then maybe something great will happen in DAI land. So stay tuned, and again, thanks a lot. Take care.